here you are. Great, Alexander.
So,
how are you today? Do you feel like showing good command of English and demonstrating some expertise in this certain field?
Probably yes.
Yes, of course. Yeah, we will be very happy to listen to both of you. All right. So, Alexander, our STO, Alexander, will you please make a picture like these two are on the big screen? By the way, speaking about podcasts and this importance for really university in Finland, universities, they have a special studio for doing podcast, and so they have a good table with 2 microphones, so that also has necessary facilities, you see, so that will be good. And our authorities also consider that it will be very, very good to have such a studio in our university. All right. So, Alexander, if you're ready, we can start recording.
Yes.
Okay, and then will you introduce what is the podcast about? Ilya, a couple of words, please, or maybe Alexander.
Yes.
So our host is Alexander. So I believe he will introduce me, and I will introduce myself later.
So, good afternoon, all. First of all, my name is Alexander. I'm the PhD student specializing in electrical power engineering, renewable energy technologies, and so on. So today I would like to interview my colleague Ilya, and I like to talk about the topic that concerns every field of the modern science, of the industry electronics, and I will discuss several aspects such as development of electronics, new materials, new innovations, and even a bit about the marketing in the high-tech world, and so on. So I would like to begin the discussion and let Ilya to introduce himself.
So thank you, Alexander. My name is Ilya, as you might have known. So I work at the semiconductor company. It's more like a corporation, and I work as a product development engineer. So my task in my team, it's I should be able to learn about what competitors are doing. I should be able to introduce ideas for the new products, develop some of the features for the new products, and sometimes I involved in testing and QA, quality assurance. So it's a wide variety of tasks I perform, and there's a lot of unknown for me, and I must learn rapidly. Each time I have a new task, I must learn a lot. So, Alexander, will you continue?
No. Let's begin with our questions on today's topic, and the first question everyone interested in is, what are the main trends in the development of power electronics in the context of the transition to the renewable energy sources?
So, in every context, they are mostly the same. These trends are the same. So now we are transitioning to the wide-bandgap semiconductors. As you might heard, we have like gallium nitrate chargers, for example, for your mobile phones. It's a wide-bandgap semiconductor, so it's also silica carbide semiconductors. In the context of renewables, they offer much better efficiency, lower resistance, lower on resistance, so less energy is wasted on the transistor itself. And we are heading towards the more efficient solar panels and battery chemistry for energy storage. As you might expect, you cannot directly pump the energy from your renewable source to the grid. So, is it a good answer?
Absolutely, and you mentioned the power consumption of the all elements. So it slowly leads us to our second question. It's what do you think? What's the main challenges in the designing high-frequency electronic circuits, and how do modeling and basically simulation methods helps us to minimize them?
So let's start from defining the high frequency. So if we talk about like megahertz scale, which I am most familiar of, so then it's the issue. Main issues are parasitic inductance or capacitance, EMI, so electromagnetic interference. And the signal integrity, for example, signal loss or jitter. So at the higher frequencies, we have the issue that the contacts, the traces could become either a capacitor or the inductor, and you should acknowledge that, you should account for it, and sometimes change the layout of the PCB or the chip itself to eliminate these issues. So if you have a long enough trace, so your signal might to attenuate, українською згасає signal. So it's an issue. So the transistor might not open if the attenuation is too high. So if we're talking about integrated circuit design, we also should account for race conditions. Українською це гонка сигналів. So race conditions are when the signals basically your signals should, for example, be synchronous and go to the transistor, certain transistors at the same time, but they are not, because length of the one trace inside of the chip is longer, or you have some buffers inside your chip, and the signal, it takes time for the signal to go through. So this might affect the logic and execution of commands. And this is an issue we've been testing a lot for projects I was involved in. So modeling and simulation, in this case, often helps to catch the less intuitive issues, like aforementioned race conditions or the signal loss. But it's the simulation, so the transistor level simulation is very slow. And we are talking about weeks worth of simulation for hundreds of milliseconds of circuit separation. So that's, I believe, all that I can say regarding these issues.
That was a very detailed answer. Thank you so much. And we tell a lot of words about the modeling, simulations, and in the context of the modern society, I have to ask you, what do you think about how the integration of artificial intelligence, our AI, into the whole design process of electronic components transform the general approaches to testing, to failure prediction, and the whole circuit optimization.
So, so again, let's define what is the artificial intelligence. So if we talk about the Gen AI, like ChatGPT or something like that, for code generation, currently it's unable to reliably do anything regarding the development of integrated circuits or development of PCBs, so printed circuit boards. It's just unable to do it right now. Regarding the failure prediction, so machine learning algorithms, certain machine learning algorithms are used in the industry since about, I don't know, like 2015 to improve the binning process, to basically find the faulty semiconductors at the production stage before the packaging, and not the packaging in the box, but packaging inside the package, like what you have seen, like this black thing you solder on the board. So it's a die crystal issues that are observed and checked if something is not okay. So that's, I believe, all. I heard a lot of attempts to introduce the Gen AI to Verilog coding, VHDL Verilog coding, but it does not produce reliable results. So you will trace back the issues. The time you spent to trace the issues caused by the Gen AI is not worth it right now. So that's, I believe, the answer for your question.
Yes, I think we all clearly understand that AI is still on the beginning of its development in designing electronic components. But what do you think now? Which modern tools and methodologies are the most effective for the hardware or software design? If we spoke about the electronics system development and design.
I'm not sure about modern, because I'm not so modern person, but what is reliable and most common or effective in our circumstances are FPGA prototyping. So basically first of all, what is the FPGA? It's a field programmable gate array. So basically it's a chip you can make into something else. So like you can program using the Verilog or VHDL, you can program this chip to be another chip. And it has some resources, it has some additional circuits inside, and using these resources you can simulate basically in hardware the chip you are making. So if we are talking about Xilinx FPGAs, which I'm most familiar of, you might use Vivado IDE for development and synthesis. So this approach gives you an opportunity to test the ideas on the real hardware. To assess the amount of resources you need for your particular idea or circuit. So it's often you are very limited in this, for example, die area. So you should account for it. And it's not one-to-one ratio as in real IC, but it's like close enough. And it counts. And to catch most of the issues, it allows to catch most of the issues way before the real chip goes into production, sometimes even years before. Although it's a common strategy, it might not be helpful when you are designing something like high speed, high performance, like, I don't know, CPU. You might want to prototype some parts of your CPU on the FPGA, but often the FPGAs themselves are limited by the clock speeds or signal timing. So when the when the code is synthesized, the insides are traced basically like a schematic, and and the timings of the signals going through the circuit, they are sometimes not even, and might introduce some issues. So you don't want to develop some super fast, super cool stuff inside of the FPGA, but it counts for the prototyping. And also FPGAs are not really helpful if you are designing an analog circuit, as the FPGAs are mostly digital only. They have like analog front ends, like ready ADCs, ready comparators, but you cannot make out of this like these cells, digital cells, any analog circuits. Hope I give you an enough answer.
Yes, that was definitely useful. And you've mentioned the programming chip. So basically, can you tell why you choose exactly this chip? So in other words, what factors determine the comprehensiveness of this electronic component in the global market? So how do innovation affect this product, the cycle, and why did you choose it?
I'm sorry, maybe competitiveness?
Competitiveness, yes.
Oh, okay. So that changes a lot. So competitiveness of the integrated circuit, let's say, price determines the competitiveness. Price to performance ratio, and I believe reliability. So from my experience, the price is most important, because no one wants your chip, no one wants your circuit if it costs a lot. It's economically not viable to buy some chips for a lot of money. So the second thing I mentioned is the price to performance ratio. So basically, it's totally unpredictable ratio, because the customer or the end user defines what the performance based on the application they're using. For example, if we speak in more simpler terms, so for the scientists, the modern GPU, like, it's worth $1,000 investment. For the gamer, $1,000 GPU, probably not worth it. So if we extrapolate to the chips themselves, the end user might not want all of the feature you've designed for the price you are asking. He might need a certain feature, one single feature, and he might go to your competitor because of this, because his circuit or his chip is basically doing this one single feature for the fraction of the cost. and the reliability, it speaks for itself. Like if your chip is basically priced as a sand, it was made from, and but reliability is very low. It's not competitive. But still, the Chinese manufacturers, they have highly subsidized the chip industry. So basically, their chips are worth almost nothing. They might not be so reliable, but still, because of their price, they're winning some share of the market. They are winning the market share because of their price and basically volumes they can produce. So I hope there's a clear answer for your question.
Yes, absolutely. That's good that we are facing the reduction of the cost of the electrical components and the world still moving on. So what do you think about the key challenges in the development of energy efficient electronic system, especially in the portable variations, or battery powered variations?
Okay, so energy efficient, it's one thing, and battery powered is the another thing. So basically, if you have the battery powered device, first key challenge is to define the parts of your chip or circuit that absolutely must stay turned on when you are operating in so-called low power mode. The second challenge is to actually find the node. It's more about chip making itself. So node is the process at which chip is made. So basically, if someone heard like terms like 130 nanometers, 7 nanometers, or 40 nanometers. So basically choosing the node with best performance to consumption ratio is the second key challenge. So for example, you might have the chip made in 130 nanometer node. Is it power efficient? Yes, maybe, if you turn it off. Because the larger the transistor inside the chip, the more power hungry it is. Like modern chips are much cooler, much more energy efficient because they're using smaller transistors. But it has some drawbacks, of course. So I think the third challenge is to properly test all possible operation modes. For example, for current leakages, you might leave some internal resistor shorted to ground. There's your power consumption goes, it's basically skyrocketing. Not skyrocketing on the scale of the battery, but skyrocketing on the scale of the chip itself. So check for the modes of operations which might lead to short circuits. For example, you might have the DC-DC converter and your inductor goes into the saturation. It's a real life example I have investigated. So basically you have a DC-DC converter and you have the inductance. After going into saturation mode, into saturation region, the inductor stops being inductor. It behaves like a resistor, basically, and a very small resistor, like 2 or 3 ohms. And during the operation, we have found out that sometimes the current goes up and stays high and drains the battery. So testing the operation modes it's important also. And it's hard to catch the things because you can have the chip issues and you can have, for example, circuit issues. It is quite hard actually to test properly, and it's a real challenge. So like something like that.
And if we expand our this topic a little bit, how do you think new materials such as graphene that's used in the modern batteries and other have the potential to make some revolution in the electronic industry? Do we have a room to invent something new and a room to work on something new?
Yes. So first of all, let's start from the beginning of the semiconductors. First, there was a germanium transistors. Then we have invented the silicon transistors. Now we are transiting from the for the power electronics, for example, we are transiting to the gallium nitride and silica carbide. I heard about graphene. I'm not into the material science, I'll be honest. But graphene has the, I believe, very low resistance. So it conducts the electricity very well. And based on this, I've read some reports that it might be helpful basically in the batteries. So it might help to increase the capacity of the batteries. It also might be used as a base for a superconductor. So do we have the room to improve? Yes, of course. There's a lot of materials yet to be discovered, and I don't know. For example, I've heard that the LEDs, modern LEDs, and certain modern solar panels with improved efficiency used materials called perovskites, I believe. So it's a tough question to analyze this, but in general, yes, we have a lot of room to improve, and even the silica semiconductors, just basic silicon, is still improving. So that's it.
Understood. Thank you. Perfect. And in the end of our discussion, I would like to get back to the beginning a little bit and ask you a final question about the importance of prototyping, simulation, especially tools like MATLAB, Proteus, and other that are not so new but still used widely in our society. So in the research, in the development of electronic devices, so what is their importance basically?
So first of all, you mentioned some tools like MATLAB. Yeah. It's important. So Simulink, MATLAB and Simulink are more helpful when you are testing some complex algorithms like motor control, something like power grid control. So basically, it's a complex algorithm that involves a lot of variables. Yes, Simulink has the ability to simulate the electrical components, physical components. It's more like physically based simulation, not the pure math. So it's more helpful for the more complex stuff. Then we have LTspice, for example. LTspice is more helpful when you want to prototype something, or check the idea, or check the issue. It's a very powerful tool. First of all, it's a very powerful tool. Second of all, it's very easy to use and lightweight. So you can basically simulate like something like operational amplifier in like minutes. It's cool, it's fast, and it is helpful when you need to quickly check the idea or trace the certain issue. There is no better tool than LTspice, I believe. I might be wrong, but also I've used for some time the Proteus. It's not commonly used in the industry, but it due to its ability to perform simulation in real time, it might be helpful as a demo tool, for example. So you have a circuit and you don't have a demonstration board, for example, but you might have your circuit in Proteus. It might be helpful to show certain modes of operation. It might be useful to show some waveforms, approximate but waveforms, and it might be helpful during the assembly and testing. So basically, you don't need to have like oscilloscope or something complex. You just need to check the voltages, currents, and that's it. So it might be helpful. Some other tools, they're proprietary mostly. And for example, Vivado, aforementioned Vivado IDE, has a simulation for your circuit when you synthesize the FPGA, code for the FPGA. You can use the software simulation. It is very helpful for digital signals, but it could not tell you anything about what's going on outside the FPGA. So it is digital only. And that's it. So
thank you. This was a really interesting discussion. So
I hope so.
Yes, I believe for our other colleagues today we touched many important things of the modern electronics, from theory to the real world aspects and so on. So in my opinion, electronics is one of the few areas where imagination exactly meets precision. So you can get a good circuit without both, without good knowledge, creativity, and logic. As we all know, sometimes one burnt transistor teaches better than 10 simulations. So thank you all for your attention. I hope yes, our dialogue was inspired for some reasons and for some people, and that's all for today. Thank you.
Thank you.
So thank you so much, guys. You've done a great job. Really, it was a dialogue of two professionals, and we really enjoyed the level of scientific discussion. You too demonstrated a high level of expertise in this certain field in electronics. So thank you, Alexander, for your wonderful questions. And of course, you have prepared very good, I think, examples of the modern state of the things in the electronics industry. And thanks a lot to our hero, Ilya. You've done great job. Thank you so much.
I hope the presentation was good enough.
Very good, very good. Now, can we also ask for some feedback of the other students present here? So who wants to say a couple of words to Ilya and Alex?